Okay, it's on.
Okay, today is March 1st, 1999, approximately 3:30 in Mesa, Arizona, Richard L. Finlinson and Levon Finlinson's home. And we're recording this because we have a visitor from Poland, Robert Zielinski.
Zalewski?
Zalewski? Okay, I came close, but Robert and I met about 9 years ago, and I covered a number of the physics projects I was working on, and I haven't seen him for 9 years, and I don't even remember where we ended off, Robert. Do you remember how far we got? It was basically about the atom, and
Yeah.
so today, to show you that I guess that I have been busy working these last 9 years, instead of starting with the micro, small electrons and protons and things like that we discussed 9 years ago, I thought I would take you from the large scale universe back down towards the small. And I guess where I want to start today is I'll start with our solar system and how this new model presents some very interesting phenomena that present day physics and astronomy is not aware of. And of course, over here on the left hand side of the blackboard, I'll put the sun, and as the center of the light from our solar system. And the solar system is so arranged that we have the first planet is Mercury. I guess I better learn to spell it right. Mercury. The next planet is Venus. Then Earth. And then Mars. And these four planets make up what in astronomy or physics are known as the terrestrial planets, T-E-R-R-E-S-T, terrestrial planets. And they have very many similar characteristics in the sense that they are much smaller than the outer four planets, which are known as the gaseous or Jovian planets. But these four planets right here have some interesting characteristics. One, they all rotate around the sun in a counterclockwise motion as we look down upon the North Pole of the sun, you might say. And there was many years ago a man named Bode, and in trying to determine the spacing of these planets, and of course I haven't got the gaseous planets here, became known as a law known as Bode's law. And you would first of all start with a number, and this one would be 0 for Mercury, 3 for Venus, 6 for Earth, 12 for Mercury. And then you add
Or Mars.
Mars, and you add 4 to those, and this gives you the distances somewhat on a generalized basis from the sun. This became known as Bode's law, which was not entirely accurate, but for example, and you divide those by 10, and this is in angstrom, or in astronomical units. And so the astronomical unit is the distance from the sun to the Earth. And in that case, you had 0.4 angstroms. You divide all these by 10, or not angstroms, 0.4 AUs is the distance of the Mercury from the sun. the next one, you add these together, and 0.7 astronomical units for Venus. Then you had Earth was 1, and then you had 1.6 astronomical units was the distance of Mars from the Sun. They tried to carry this out to the gaseous planets, and one of the problems they had is that between Mars and Jupiter, they kept trying to place a planet, because using Bode's law said that there should be a planet between Mars and Jupiter, and for many years they searched for Planet X, is what they called it. At the present time, this is in the area of the asteroid belt, and the asteroid belt, many reasons have been given to account for why the asteroids are there, and some of the things as well, there was a great collision, and these small pieces resulted. But I want to spend a little more time here with the planets themselves, because as these are in the process of circling the Sun, some very interesting characteristics can come out. One, we have a situation where Mercury precesses, and the precession of Mercury is what Albert Einstein partially solved the equation as to what to account for the fact that Mercury was actually traveling around the Sun at a faster speed relative to the other planets. And the general theory of relativity accounts for part of the precession of Mercury. The other thing that Einstein never mentioned is that the second planet, Venus, as it was traveling around the Sun, had retrograde motion. All these particular planets here, Mercury goes this way, the rotation of the individual planet, Earth goes this way, and Mars goes this way. So the great question that comes out of the precession of Mercury, Einstein solved partially this problem, but he never really had a theory that accounted for the retrograde motion of the second planet, Venus. So as it's traveling around, Venus is spinning opposite the rest of the terrestrial planets. Mm-hmm. So, Dick, do you want to cut that off for a second?
Sure.
One of the great questions of the universe is tied up with Planck's law and Planck's constant, and this has been a great help in finding energy levels in compounds and things like that. But Planck's law also has probably led people astray as far as the greater truth, and I want to demonstrate that a little bit this morning. There's basically in the realm of physics, there's two laws. One is the Jeans-Rayleigh, and the other is Wien's law. And this one, the Jeans-Rayleigh law, the curves apply to high energy levels, and as scientists are tracking these energy levels, Jeans' law, the curves fit. At the same time, Wien's law is the low energy or frequency, more in the realm of radio waves. And Planck came along, and through not any derivation, was basically a lucky guess, and he derived Planck's constant. And Planck's constant is an oscillator law of energy. That it's a frequency law, and how many times energy these beats. And what Planck did is he took these two laws here and said, okay, Planck's constant applies to both cases. But what this very act of applying it to both cases did, it submerged the fact that within the elements themselves, there is matter that's high energy and there's matter that's low energy. And what Planck's constant is doing is measuring, if we measure from the high energy down or the low energy up, that Planck's constant fills that gap. And basically what they do is they'll either put a plus or a minus. So depending on whether you're starting or this is Planck's constant's the bridge between these two energy levels. Yet with this in mind, science really never followed up on this in quite the same sense of the current theory of light is that light is a series of photons and a bullet type theory that there's gaps in between these photons. Well, this at the present time we have the wave particle theory of light, and yet they've never been able to they use both theories is what it amounts to. One is photon theory of light is used in some situations and the wave theory in others. However, the question now comes, well, which are we going to use? And if you look at a electromagnetic wave, there's an oscillation, and this is called the electropositive.
I'm wondering.
When I use this wet or something,
that's
Yeah,
exactly what
Probably, maybe we
it's,
better just try a
it's
dry one.
just-
dry. I think the dry one. I think
Yes. The
when I use wet, I just fade out.
Yeah, and
Yeah.
another thing, have you finished that
A
first?
little bit about light
Right.
here.
I figured that's what you're doing, but I thought,
Electro.
where's the rest of it? Okay, now start.
So light is a transverse wave. A transverse wave has two components. The electropositive sinusoidal wave, and then at a 90-degree angle here, while this is traveling, there's another component, and it's a little hard to, but this is at 90 degrees, and this is the electromagnetic. And this is the minus, and this is the plus. So as we see light travel or energy travels in a transverse manner, and it has two components: electromagnetic negative component and electropositive component. And what physics has done is they've basically said all of the spectral lines that have come from matter, they have not distinguished between electronegative source or electropositive source. That they've said, okay, an atom is neutral, and the spectral lines that come from them of different lengths, it really doesn't matter, it's just a spectral line. And this is hiding one of the great things of the universe, is that light can come from a negative component as well as a positive component. Thinking of it more in terms of kind of like a heartbeat, that you have one side and the other, and so to get eventually back to the planets, I have to give you a little bit along this transverse wave, because as matter interacts with light, we find that on one side there's a gap in the positive side. Let's say this is the positive side, there's a gap, and the gap is a negative over here. And in the negative, there's a gap here also. Now, if I describe this from the sense of an atom here, what happens is the periodic table breaks all elements into families of 8, and what we find is that this is plus, this is minus, this is plus, and this is plus. This is minus, this is plus, this is plus, this is plus, but all this right here is in a negative field, and so the signs all change. Okay? So this becomes a positron instead of an electron. This electron becomes a positron, so this becomes a this, and so either side of the Pulaski model, you have 3 of the positives and 1 negative, and you go to the other side and you have 3 negatives and 1 positive. So as they're recording this electromagnetic wave or the photon theory, they either have it on they've either got it on a positive charge or a negative reading. And so what that does, that then develops a series of gaps depending on the polarity of their equipment. When we take it to the ultimate source, back to the atom, this becomes what we would term as the Planck oscillator. It oscillates between positive, negative, positive, negative, positive, negative, and does it at a really huge number times per second, is the Planck's constant oscillator. But the basis of it comes back here to this basic atom here with these subcomponents, and what happens is that when it flips over one side or the other, it immediately repels, in the same sense that good cannot stand bad and bad cannot stand good, in the same kind of sense. And so this oscillator is going back and forth. Now, I had to cover that with you to then go back to Mercury and the Sun and some things here. Okay, here's the Sun. Here's Mercury right here. And here's Venus right here. Remember which way Mercury?
Over there.
Okay, Mercury rotates this manner,
Opposite.
and Venus this manner. So several things happen. Mercury has this precession, so the precession is an advancement it goes faster than the normal. Okay, precession, advancement in a positive field. That's right what happens over here. Because in this model of the atom that we are working with, every other octet or pie-shaped area of the atom, every other one of these have negatives mixed in here somewhere or the other with the spins, spin up, spin down. But in this one here, there are no negatives. So the negatives hold us back in the same sense that if there are no negatives in the energy that comes from the sun, that are based on these wavelengths here, Mercury gets more energy and precesses ahead of the other planets. At the same time, this second octet is a negative in a positive field. And this is what causes Venus to rotate retrograde in a manner exactly 180 degree opposite than Mercury or the Earth or Mars. Okay? So it comes from the matter itself in the universe, and yet everything you read about Venus is that, well, it got started and had a collision eons and eons ago, and it started spinning in the wrong direction, and it's been doing that ever since. It really hasn't. That the energy that comes from the sun, it radiates from the sun, has these frequencies built in here that have different, you might say, little pockets or discrete levels. And so the first level here, there's no negative. This is why it precesses. And the question comes, well, okay, how much does it precess? And it precesses between 6.5 and I'll say 6.7% more than these other planets. How do I know that? Because superconductivity, it takes about 6.6% more oxygen atoms to create a superconducting level of copper oxide. It's like there's an imbalance there with copper and oxygen, and they have to add about 6.7 to 7% more oxygen to make it a superconducting field, and that's the same amount that what causes the precession of Mercury. Now,
But if I understand it, so then there should be one more planet which is going the same like Venus, yeah?
well, they're in the terrestrial planets. This is analogous to the
Yes.
terrestrial planets over on this side.
Mm-hmm.
Okay, now the next question is, okay, what do we do with all the rest of those planets out there? And that's what, let me erase and cut.
Turn it on.
Okay.
Okay.
These are the Jovian or gaseous planets. Here's Jupiter, Saturn, Uranus, Neptune. Now you notice, Robert, I've left off one planet, Pluto.
Yep.
And I was meeting with the assistant director at Kitt Peak, and he asked me, he said, do you think that Pluto's a planet? And I said, no, it's more in the realm of a large asteroid. He says, well, that's exactly what I think. He says, I think there's 8 planets. And I think there's 8 planets because it fits into the same, more or less, energy levels as the different families of the periodic table do. So Jupiter here is the big, huge one, and of course next to Jupiter we have Mars over here, and the question is, well, why are they this huge size and get to a smaller size here? Well, what happens between Jupiter and Mars is a field change or an inflection point, and this is when you get into a negative field, everything runs backwards. Now, if a normal field, we would say, okay, we were generally progressing, and Mars is not quite as big as the Earth, but we were generally progressing from smaller to bigger with the terrestrial. And now in the Jovian, we're progressing from the largest to the smaller. And so the normal sequence would be Neptune, Uranus, Saturn, and Jupiter. Okay, can you, and the reason they're in the sequence they are is because they're in a negative field. You get to the fourth planet, and there's a field change out there. Okay, so if there's a field change, everything reverses, and that then means this one comes in closest. When I say it reverses, this is in a negative field and everything running backwards. This is the most negative. This is the least negative. Okay. Now, how do I know that? I mean, I can make a statement, and there's two or three ways that are evidence of a field change in these Jovian gases. You want to cut for a minute? Let me just wipe this bottom part right here. On Jupiter, Jupiter has what is known as the Great Red Spot. And it's not too far from the equator, but lo and behold, the polarity of Jupiter is different than the polarity of this Earth. This is the polarity of Jupiter, whereas we tend to think of our Earth as the North Pole, South Pole. Well, on our Earth, we have a hole down here at the bottom. Do you know what that's called? Well, they talk about it as the ozone hole. Okay, and it covers parts of the southern tip of South America and into the Antarctic area. So it's very, very natural to say, oh, okay, this is all caused by hydrocarbons and things like that. Yet, I dare say most of the hydrocarbons, there's very little down there at that point on the Earth, the southern tip of South America. There's a hole there, and this hole ties in with our model. That if there's a place where there's something in the universe, there's also a place where there's nothing in the universe. If you want to look at it that way. So as we move from the terrestrial planets to the Jovian planets, and we move from a positive field down here, what's going to happen to a hole? Okay? The hole that would be like down here, the bottom, here's our negative down here. If it were like on Earth, the hole would be here. But instead, the hole is close to the equator of Jupiter, which means then that there's a negative field effect difference between Jupiter and the Earth. And this hole right here that has been there observed for 400 years or more by the earliest times Galileo is somewhat against the equator, not exactly, but it's pushing the equator. And it stays, they've had all sorts of theories as to why it's there, and doesn't ever, it always stays in somewhat the same place, because it's very analogous to the ozone hole that we have here. But when you get into a negative field, everything starts reversing. So I'm giving you kind of the simple cases of what's happened in a negative field. Now, cut around the sun in the same direction, all the planets all go counterclockwise around the sun. But you you start getting into some of these, and there's some of them that are retrograde here also. It's not quite as simple as I wanted to make
This
it.
was my question, because should be.
What's that?
Should be. Some should be.
Well,
retrograde.
yeah, the one that's the most that has the craziest are these two out here, and they are the ones that are the most negative, because this one here is instead of there being a direct north-south sort of thing, it's really looking at the plane of the solar system. It's like it's gone bonkers. They don't know, it has a really strange rotational thing. So the question is what causes these axial tilts, and these are all somewhat different. And I think it goes back to the atom, the Pulaski atom that we've talked about, and part of it is what is known as I want to say bound waves, but that's not quite the terminology. But I can explain it a little more later. But I want to get. Are we still off? We're on.
No, we're on.
Okay.
It doesn't matter, just
Okay,
let's get it all on.
The thing that I wanted to touch bases on is between Mars. We'll say Mars is here, and Jupiter is the asteroid belt.
Mhm.
And what I earlier indicated is that there's a change in the field, that this is a positive field for the first 4 planets out, and there's a negative field for these planets here. And the asteroid belt is approximately halfway between these 2 planets. And there's a term known as albedo. Albedo is reflectivity of light.
Mhm.
And there are asteroids that are over on this side that have high reflectivity, and those that are on this side have low albedo or low reflectivity. How do we know? We've got pictures here. And they measure the reflectivity off these asteroids, and they're saying, gee, these over here are all bright, and these over here are dark, dull, they're very absorptive aspects. The other thing that ties in with this asteroid belt and this change in fields between the terrestrial planets and the Jovian planets is the comets that we see. Comets, suddenly somebody finds in Japan, or somebody finds a new comet that came out of nowhere, is a hero for the day, or as long as the planet comes along. Well, what happens with a comet, they suddenly reach a certain point where they brighten, or as they're leaving the solar system, they suddenly blink out and diminish, like a candle going out. And my thesis is that they have crossed from the negative field into the positive field, and all of a sudden there's life and light and a brightness there, and so all of a sudden they're easier to see, and that's why, gee, it came from nowhere, we didn't see it, and all of a sudden it got approximately 3 astronomical units from the sun, and this positive field is on this side. So this line right here ties in with not only asteroids but comets, and the other thing that ties in with comets is that the comets, most comets have 2 distinct tails. One, quite a bluish white tail, and one a red scattered tail. A lot of the planets now, or the comets, and what happens when they cross this? You see the one tail brightening and the other tail not brightening as much. I mean, it's so this is an important point right here. Now, the that occurs about 3 astronomical units from the sun. So that is between here and Mars is where this and the comets do brighten. Now, with the Jupiter and the things that we see on Jupiter, we find that there are distinct zones that occur.
Mm-hmm.
You see a lot of pictures, and I'll show you some in here. And the question is, why do they have distinct zones on Jupiter? And the distinct zones come from the fact, just like the different octet 1, octet 2, octet 3 of the Pulaski model has different energy levels, we see the same thing happening in here. And you could say some spin up, some are spin down,
Mm-hmm.
and there's these zones have positive and negative components to them, just like going back to the original atom. This also accounts for one of the big things they're looking for in the universe is missing mass. Like
Mhm.
90% of the mass of the universe is missing. Well, they've misnamed it. If you take all the mass from here on out and say in the gaseous planets that this is mass in a negative field, you don't have missing mass. I mean, you have mass that's been misnamed, I'll put it that way. And we've talked about the giant red spot. The other thing they have a great problem with is known as differential rotation.
Stop, wait a minute.
In the Pulaski table, we have once we cross over the barrier from the positive field and we flip over to the negative field, there's what is known as a binding energy drop. There's a
Mhm.
real huge drop after carbon, and you go into the nitrogen field. Now, scientists have said, well, this is bound up mass that goes into atomic energy when we blow everything apart. This is extra energy. But what is a better explanation is that once you go over that hill between carbon and into the negative field, the negative field carries much less energy, and it's at that point where it's like there's a missing energy gap right there, because what happens is in the positive field, all of these are pulling towards the positive pole, and you get on the negative field, everything's pulling towards the negative pole. That leaves a little area, octet area here, that is more electromagnetically neutral,
Mm-hmm.
or missing energy. And it's just after you go over that flip in there, because it doesn't take it right up to the pole part. It's actually leaves a little pie-shaped gap in there. It's actually
Want
kind
the
of,
color? Oh,
well, I was just going to say, it's actually when the energy builds up and then you go over the pole, instead of it being right here, this is all pulling towards the negative down here. This is the area that has very, you could say there's an energy gap
Mm-hmm.
in there.
that ought to have been on the tape,
It's fine for right now, I think.
you know,
Okay.
showing,
Well, now, the next planet here is Saturn, and to tell you the truth, Robert, Saturn was the one that got me going into the Jovian planets, and what happened is Saturn has these rings.
Yeah.
And the rings of Saturn have certain rings that have gaps between them. And one, for example, is the Cassini division,
Mm-hmm.
or the Cassini gap, he was a Catholic priest that noticed there's space between these rings. Now, contemporary thinking is, well, why should there be a gap there? And the gaps, the rings of Saturn, they're named a little bit different because at the particular time the first one was called the A ring. This was the outer one from the Cassini division. It seemed the brighter, but in the long-term Hall of the different reflectivity of Saturn, the B ring is the brightest ring. So this Cassini division then becomes analogous to an area that is very electromagnetically neutral or not much happening. And on the big solar type thing, it's analogous somewhat between the Mars, Jupiter, yeah, where the asteroid gap is. But in here, we have some of the same things in the Cassini division, is that you have energy with certain gaps, and I haven't carried all the rings out. But these all tie in with the Pulaski model, that there's certain things happen that create a gap. And you know, it's like modern contemporary science doesn't know how to handle
Did you put that
some
up
of the gaps.
so that, just put that up so that the movie can show that?
Well, it's hard. It's
I know.
really hard to see here. All I'm just saying is there's the A ring was the first one discovered. The B ring is the brightest now. But between the two, there's the Cassini division, and these become very hard to spot, the inner rings, and the reason is because they have higher frequencies.
Mm-hmm.
And the higher the frequency, the harder it is to for them to even see it. Okay. The at the present time, there are basically 7 rings. They're finding numerous rings with all of the planets out there. Now, this little paper right here, can you see that, Dick?
I can zero right in on it if you hold it out.
Okay.
Yeah, that's.
This shows all of them together here. The sun is not depicted, but Mercury, Venus, Earth, Mars, these are the terrestrial, of which between Mars and Jupiter is this field change or an inflection point, and the Jovian are, the biggest is Jupiter, Saturn, Uranus, and Neptune. And really, if we weren't in a negative field change there, the size would be reversed. Okay? Because the gaseous ones, they just don't have the inherent capabilities of becoming terrestrial, I guess, is one way of putting it. Now, the
And are these all going the same?
yeah, they're all, and that raises, I think, a question that you maybe alluded to, is, well, notice that these are all going the same direction, even though the second planet, Venus, is retrograde.
Mm-hmm.
And some of these others out here have highly retrograde elements, but the poles of them are so crazy it's a little harder to depict. And what this really depicts is that the positive energy of the electropositive, I showed you that little sinusoidal wave at the beginning.
Mm-hmm.
There was an electropositive portion and there's an electronegative portion.
Mm-hmm.
They are not equal or in balance.
Mm-hmm.
There's an asymmetry there of energy, and the positive has more energy than the negative, and that's why all of the planets are under control of the positive, even though there are some that are spinning backwards because of their positional characteristics. So that raises some interesting questions as to what happens when we look at planets up close and way far out. And so I'd like to now go into Newtonian gravity, and I think he certainly wasn't a contemporary of yours, as Kepler was Polish, is my recollection. And Kepler worked out a lot of the orbital characteristics that Newton later worked on with gravity. But let's clean this off now.
You know, you can put your charts on a deal like that and use a felt tip,
Yeah, and just
black, heavier marker,
and then show up better.
and they'd show up better, and,
And
then
then
you
we
can
just turn
hold
pages,
them.
just-
You can just hold them
Okay,
out,
yeah.
and that'd
But
be
this
fun.
is working quite
Well,
well.
yeah,
I
well,
think.
we're gonna have to
Yeah.
experiment. You know, it's
Right,
okay.
but
Now,
zero in.
now you remember.
You ready?
Are these
no, just a
flips
second.
in-
No, just a minute. Okay. Okay.
Those things don't show
Yeah.
much anymore.
Okay,
so-
remember-
The red ones?
Huh?
The red ones, we cannot see the red ones?
The red ones don't show
Are you
here.
able
or-
to zero in on that?
No, I'm
then?
I'm saying the stuff
There's
on
other
the
stuff.
table don't
Oh.
matter. That doesn't
Now,
matter.
Robert, with the different planets of the terrestrial planets, the small one, Mercury, then Venus, then Earth, and Mars. Question is, well, why isn't Mars a continuation bigger than Earth? I feel like that this barrier between positive and negative is affecting it, and that's why the size is not as large as here. But when you start taking the charge equivalents from the Pulaski table, the first one is positive, the next one is negative. Remember, this is the retrograde, and these two are positive. Then the gaseous planets. Actually, if we continue it now, this shows the sign change.
Yeah, it should be positive.
Yeah, it's actually negative, but because it's a
Yes.
negative field,
Mhm.
negative times negative is a positive. So positive, negative, negative, negative on that. Now, the other thing that happens here is the Cariolis. Coriolis effect. I don't know if that Y is correct in there, but anyway, this is the effect that, simply put, is that when you flush the toilet in the northern hemisphere, it turns in one direction, and the southern hemisphere it goes the opposite way, and
In retrograde.
yes. Now in the north, just like we have the Coriolis effect on our Earth, I think that there is a somewhat similar situation with the Sun.
Mhm.
And I work with a very good Catholic fellow that he's a retired lieutenant colonel, and I asked him one time, what happens when you fly across the equator? And he says, well, that's easy. We adjust our navigational instruments about a little less than 7%. So what he was saying is he crosses from a northern to a southern, he has to account for, he called it the Coriolis effect, and what we're saying is that if you think back to the Great Red Spot of Jupiter, there's a difference between the northern and the southern hemisphere. And what they've recently found on Project Soho with the Earth is that there's a field anomaly. And what that is basically, what we're talking about are some of these solar anomalies, but the North Pole of the Sun has more energy than the South Pole of the Sun. And this is one of the things that's happened with the satellites is the why should the North Pole have more energy than the South Pole? And yet the North Pole of the Sun is a positive field and this is a negative field. Right here.
Mm-hmm.
Now, what happens is that this then leads to certain movement of wind in that, and you get the El Nino and the different weather creations that occur is actually part and parcel of the correct concept of the Pulaski atom. And you get electropositive here, electronegative there, and a lot of it is based on the Coriolis effect. Now, the thing I'd like to just take for a second and talk about was the great contribution of Kepler, is his orbital observations and the way planets orbit. Do you remember what he found? He didn't find a circle, did he?
No.
He found an ellipse. But an ellipse has a foci.
Mm-hmm.
But the other thing is every ellipse has really two foci. They never talk about this one.
No.
And so the question is why did, well, if an ellipse is really two and they've never found the other one, how does an ellipse work as far as the planets, etc.? And it makes a lot of sense if you start thinking in terms of the sun over here sending out energy, and there's positive and negative energy. The same thing as you have here. You have a positive ellipse and you have a negative
White was too.
ellipse, and that this is what causes an ellipse. But in most of the calculations you see people doing on orbits, they assume a lot that it's just a circle. Okay,
Yeah, but it's not.
it's not.
But this is like a matter. Yeah. This is matter. Usually.
It's imaginary. It's an
Imaginary.
Both of these are imaginary numbers, and yet every ellipse has to have a foci. It actually has to have two foci, but they'll take one, and so as I got contemplating about the different planets and that, the thing that happens is the first thing is you feel like, okay, this is a pretty constant travel around the ellipse as it gets.
Mm-hmm.
But what you find that it is not constant that closer to the sun is traveling much faster.
Mm-hmm.
Out here it's much slower. And the other part that is kind of crazy is you find that all of these planetary orbits have retrograde characteristics.
For all planets.
All planets.
How is that revolutionary? Absolutely.
Okay, all planets have retrograde characteristics, and some of them are absolutely huge. The number of days that they are in retrograde motion. So for example, and all they can say is that the retrograde motion, it's because of our position on Earth, that it's an optical illusion. And
Now, if you lift that up, it can zero in on that one page.
well, okay. Let me just find the. Let's see. I've got it. I had two of these books, and one of them I cut down.
Shall I try to find
No,
it while you're
well,
talking?
no, well,
Just
just
kind
okay. I'm right now. I'm talking about retrograde motion as being something that's been passed over as a more or less optical illusion, but is very important to planetary orbital mechanics. And for example, the conjunction with the Sun on Jupiter is like 399 days, of which after the 140th day, retrograde motion begins, and retrograde motion ends 260 days after. So there's 120 days of the roughly 400 days of Jupiter's traveling around the Sun that it's in retrograde motion.
Okay. So what was my question at that time? Because it should be some retrograde.
And they all have retrograde. They all have retrograde. But the point I want to make is they still all go the same direction around the Sun, because the positive side is stronger than the negative side. Yet when you get out into those outer reaches, and they all have negative elements in their orbital characteristics, and they kick in, and the retrograde motion is more than just a figment of a imagination. Now,
It isn't an illusion anymore.
yeah. Now this right here, we talked about the asteroid belt, and this is taken from the Cambridge Encyclopedia of Space and that. And if you'll notice right
Some
here,
are bright and some are dark. Yeah?
that's right. And the part of the asteroids have very high albedo, and the ones farther out beyond the 3 astronomical units, further out from the Sun, they're just dull and dark. And that's why I'm very certain that there's a field change there, Robert. Now, do you want to cut for a
Cut,
minute?
Dave. I think it,
Main value. That's talking about Mercury.
Mercury, yeah.
Yeah, and see, what we're saying is there's between 6.5 or 6.6, yeah, of difference, the energy between one side and the other. Now, this is about the SOHO thing here. Now, there's some other things that I haven't got into that are a little hard to explain, but one is the Schroeder effect. And it's one thing to look at those far planets and see things because you got more time when you're looking at the closer planets. But I want you to think of this. This is the phase anomaly, or Schroeder effect. And this is talking about Mercury. Another kind of observation that's worth making is to attempt to determine the exact time of dichotomy or half phase when the terminator is straight, though these are not always equivalent terms. This occurs when the plane-centric angle between Earth and Sun is 90 degrees. The planet then looks half illuminated to earthbound observers. The time of dichotomy and greatest elongation, just talking about the orbits now, roughly coincide during an apparition, but do not coincide exactly because of the eccentricity of Mercury's orbit. Although the times of both dichotomy and greater elongation can be predicted exactly predicted. Oddly, the predicted and observed times of dichotomy often disagree. Why the disagreement in the predicted and observed times of dichotomy? It was Schroeder who first noticed this discrepancy when he observed the planet Venus during 1793. has since become known as the Schroeder effect. It's been evident that Venus, since that time, and Mercury sometimes shows it. Dichotomy occurs late for Western elongations and early for Eastern elongations. The difference never exceeds 5 days, if that for Mercury. Now, if you think in terms of part of this orbit here
Mm-hmm.
being in a positive energy mode and at times in a negative energy mode, it means that there's time is going to vary in some of these things they've seen, and I'm very certain that the Schroeder effect is tied in with the Pulaski model of the atom. That's more about, and you see that with the inner planets. Here, for example, here's the this is the Mercury, the flyby of Mercury, and they've got different times in 74, etc. And then right here they've got this loop business
Mm-hmm.
with Mercury.
Exactly like in the atom.
That's right.
Say that
That's
again?
right. Exactly like in that.
Exactly like in
Okay.
the atom.
Let me just read this. Now, this is from this Cambridge Encyclopedia of Astronomy, and it says, Mercury. There will be a period of about 8 days at perihelion during which the path of the sun is very peculiar. During this short period, which occurs around midday with respect to the Mercurian day of 106 days, the observer will see the sun move very slowly, then stop, and set off again in an opposite direction. And that's the loop.
Yeah,
Is it?
exactly.
But you see how they missed it.
I
Okay.
remember the day Paul called me and he says, the main thing, the thing that stands out in my mind in this work is that positive is stronger than negative. Always this, he says, I'm hitting it all the time, the same
I know.
amount.
I mean, when you see everything that you're taught in math, is it positive equals
Yes.
negative, and yet all of their equations are equality equations, and that's not the law of God or the universe or anything else. Is that positive is greater than negative, and you when you start talking like that, they look at you like you're real strange, you know. But this has a lot. Well, this shows the current thinking of the retrograde loop here. That that is depending on where we are is where this here business occurs. And it appears to go backwards. So they're saying it, but it's like it's they haven't got it incorporated into any of their equations. For example, the gravitational equations of Newton.
Mm-hmm.
He's right on a mean annual basis,
Mm-hmm.
but he's not on. If you're trying to pick out a segment, that a lot of things are happening in those
and
orbits.
what's happened is where when Bohr's electron distribution chart, where they skipped over those little numbers, that little changes that have occurred, you know what I'm talking about, Robert? And they told everything, and yet they didn't know what it meant. And by eliminating those, things went in orbit. But putting
Well-
those there, it shows the
Yeah, here's
reality.
the Jupiter thing. I think this is quite interesting in the sense that here's the red spot, here's the South Pole.
Dick,
It's the exact opposite.
Mm-hmm.
I was
Well,
just
we've
saying-
already talked about
Oh,
this.
okay.
So I'm just saying, here's the red spot right here, and here's this differential rotation. Why is it that some parts, these hatch marks, supposedly when they read them from Earth, are rotating faster than the others? So interesting one. The Saturn rings. You'd think if there was an electromagnetic ring around all of the Saturn rings, notice that there's a big difference. They don't match up. Well, why don't they match up? Just like in the atom, the Pulaski atom, there's these discrete levels that have higher or lower energy than others.
Mm-hmm.
And you get this with these part of the Saturn ring phenomena. Oh, I don't know.
This is nice, the way you got it
Well,
mixed up.
I got so big and bulky. I hated it.
Yeah, oh, you had lots
Uh,
of hooks and lots of things.
Did I talk to you much about Balmer's Balmer?
No, I don't
And
remember.
her spring Russell also.
Yeah, I haven't done much on that for quite a while, but I'm trying to think of the Balmer stuff. Right now, I wanted to talk, Robert, a little bit about the hydrogen atom spectra. In the hydrogen atom, we have the hydrogen alpha line, which is the main red line of hydrogen spectra. For example, over here, here's the red line of the hydrogen alpha, and they use that as one of the dominant lines of the hydrogen atom, and yet it's the longest of that particular series is wavelength, and what turns it red is that it's flipped over past the barrier into the longer frequency, and so if you come on this side of the hydrogen alpha line, then you come into the beta, gamma, delta, etc., and you get what is known as the Balmer jump, and the Balmer jump, or the Balmer decrement, is an area that, as we go to higher and higher frequencies, it eventually comes into what is known as continuum spectrum. And in our here's the positive pole, and when we get lines that come over from the negative, these are longer and have, we just call them red aspects, or I call them red aspects, and the hydrogen alpha line originates over in this area, that particular line. When it goes back, and that's why it's red. But the lines that come from this area right in here become what is known as the Balmer jump, or the Balmer decrement, because each one of these lines, as you go higher and higher frequency, because they're shorter, the distance between the source and the pole, they get to a point here where they call it the continuum. And what the continuum is basically they run into this octet 2, which is all negative stuff, and so the lines system of the positive lines gradually fade out and end right in this area. And this is what this depicts right here, Robert. That eventually you come to this continuum aspect. Here's the hydrogen alpha, and the lines get shorter and shorter and closer together, and then they come to the continuum. Well, this is the area where it's spin down and all negative, very analogous to to Venus's backward spin. And so the positive aspects of light diminishes when it is impacted by the negative. Well, I don't know, Dick. I guess I'm about burned out right here, right today.
Why don't you do the Hertzsprung Russell? And that to me is very interesting.
Well, let's. I think there's something even better than that. Do you know what the mass luminosity relationship is?
Oh.
It's this will blow your mind, Robert. Leave it going, Dick. Okay.
Have you got it on, Dick?
Yeah. The mass luminosity relationship says the higher the mass, more light comes out, more luminous the object. And that's why, as they classify stars, the most luminous stars are type O. O, they have different classifications. O, B, A, F, G, O, B, A, F, G, K, and M. And the way they learned these different classifications, Robert, here in the United States, is O, be a fine girl, kiss me. So what they find, there are many of these stars in the lower part that are not as bright, but there are very few of the type O and B stars. And the type O and B stars, what I've discovered, well, what they say, that they're the type that are going to burn themselves out, and they're the short-lived because they are so bright and luminous that they're going to burn themselves out first. And they're 180 degrees off. The type O and B stars occur in octet 1 of the Pulaski table. The reason they're so luminous is there are no negative spin down of any matter in that area at all. And so the thing that happens is with the huge amount of light that these type stars generate, they say that the radius of these stars are as big as our universe. Totally not true. It's just that the light, there is the light is not all the same light. There's the light of the devil, or there's the light of God, and there's other lesser lights in between. And one of the big things they really cannot account for is why there are so many of this dull stars of the what they call brown dwarfs and red dwarfs. There's just innumerable ones out there, but there are very few of things over here on this end of the category. Very similar to the 76 section of the Doctrine and Covenants. But the mass luminosity relationship says, okay, if we have so much matter, it's going to generate
more light.
So much light. But you can have, just like the light of some of those asteroids, some light, or some matter absorbs light, and some matter generates and is highly reflective of light. And anyway, this is a big relationship in astrophysics, and it's totally fallacious because they're looking at all light and all matter as being singular, being the same, and it really isn't. It's that the reason they say this is going to burn itself up is they figure out, okay, the matter has so many years, and that the nuclear energy in this is going to go on for so many years. I don't think the nuclear energy thing is it at all. But with what Lon wants me to cover just briefly is the mass luminosity relationship. Two different people, an American who is a professor at Princeton, and a Scandinavian, Einar Hertzsprung, who studied in Holland, independently plotted the mass luminosity relationships. And this became known as the Hertzsprung-Russell diagram. And the Hertzsprung-Russell diagram is basically has a they call it the main sequence. Okay, main sequence, and that most stars fit on this main line. and that they break away, and I'm going to give you, there's the red giant branch, and they show this has a kind of curve up here, and then the type O and B stars are up here, very, very few. But then in this area is known as the Hertzsprung-Russell gap. And that between this is there's actually a measurable gap,
Mm-hmm.
and that in this gap there are variable stars. Now, one of the things that Helen Plowski's model had was that there were, remember in Octet 1, Octet 2,
Mm-hmm.
there were, what were they, sliders? That
Yes.
Okay.
All that activity going on.
Yes.
I feel very certain that this is related to the variable stars that occurs here, and there's two different types of variable stars in this Hertzsprung-Russell gap. There's a type 1 and a type 2, and I think that it's interesting that in her model the sliders occur
Sliders too. Yeah.
in type 1 and type 2, and they can distinguish between those two. Now, the other thing that happens is they try to create evolution out of this. This is the main diagram of contemporary, the evolution of the stars, and eventually we start out, they generally start out here, become a red giant, and you go over here, and then you come back in here, then you go back out here, then you go over here, and then you come down here, and then these are the white dwarfs down here. And these are the ones they can hardly see, have very little light, very little reflectivity. If you think of this in terms of the polarity line in her model, the parts of the atom that are down in this lower left-hand side are the most negative,
The
absorbing type. Exactly, absorbing type. And over here we have a thing called population 1 and 2, and this is where planetary nebulae can come from. And they say that this is a big evolution. We start here, we go up here, we become variable stars, we go back and forth, we start to flare out, we spend up all our energy and come down here, and it's all hogwash. But it's what's believed by today. And the thing that
Isn't that exciting?
and the thing that's happened is they say, okay, we've got population type 1 and population type 2 stars, and they're just nearly the same, but one of them are the old stars. They say are 15 to 20 billion years old, and then there's the type 1, which are like 5 to 7 billion, something like that. So within astronomy today, they have a huge argument about how old the universe is. And depending on what they're measuring here, whether it's a type 1 or type 2 star, you can make a strong case either way. But what I'm saying here is that there's kind of a little bridge area. And you remember I was showing you in let's see. Well, this'll help right here, I think. Yeah, turn right to it. This shows the two different types of variable stars, and this shows that there are some of these that come over into the negative field. Okay, but when they go into the negative field, the sign changes, and even though they're similar in their negative field, one becomes older than the other just because of a field change rather than than a true
Mhm.
evolution change. So anyway,
Well, and then that branch that goes over towards you, Robert, that of course is such an energy drop from those two octets. up
and really
there.
this is where the Savior, when Lazarus said, you know, can I want to go to the poor man and the rich man at the gate and all that, and the guy says there's a great gap between you and me, and there's a great gap between those that are going to go to the type O and D type
so there
stars.
Are 3 divisions.
So there is
there.
an actual physical gap that you cannot cross once this earth is over.
And there's those 3 divisions, the very bright stars, and then down
Well,
below there.
Here it kind of shows, there's 2 or 3
Right.
things right here. Here it shows the supergiants and the giants. This is kind of the red giants. Here's the white dwarfs down here. But there's, where am I at? Here shows the 2 different types of variables, type 1, type 2. They're very similar, but they're different, and they distinguish them, and that's between octet 1 and octet 2 sliders, I'm quite certain about. And I wanted to find the big blue bump.
Yeah, that's interesting.
It might be in one of these other books, though.
Can't get over how much easier this is.
Oh yeah, it's a lot easier to handle. Yeah, it's got to be in one. I think it's probably this one. Yeah, there's a whole area we haven't got into about the.
Can you show us how gravity is working?
Well, gravity is here, but
It's right within the
yeah, basically,
spin, isn't it?
well, you got the 2 forces. You got the positive force and the negative force. But what you have is that in the atom, those 2 throughout all eternity are nearly matched, depending on whether you're in a negative field or a positive field. It can only be a half a wavelength difference. You gotta have both. You know, there's opposition in all things. There doesn't say their opposition is equal in all things. It says there's opposition in all things. And that once you get, the best way of describing it is once you get into that negative field and the frequencies of the hydrogen alpha, for example, remember me showing you that, that they are not aware that there's a high frequency, low frequency aspect to everything. And
And so it's basically flowing together, the magnetism, isn't it, of the 2?
well, I don't
Or it's just
know.
built right within the
Yeah,
system?
it's within gravity. If you want to say gravity is
it's
the
just-
negative component. I mean, but you also get up there and you see, for example, Hertz did one of his very first experiments with either sodium or lithium. I think it was sodium, and he told about viewing the electrical gap of the sodium atoms, that 1/2 wavelength was whiter than anything he'd ever seen on the earth, and it was right from that part of the atom that there's no negative diminishment of light in the area of the sodium atom. I still can't find what the anyway.
Is it in there?
I don't know. In this book, Mathematical Astronomy Morsels by Jean Mius, there's quite an interesting thing that shows the different orbits, and the orbits, when they're describing them, have either an ascending or descending orbit. And so he has a directional arrow that's and he's numbered each of these 1, 2, 3, 4, 5 on up to 17. But the interesting thing is that 1 and 8 are exactly the same except a mirror opposite. Okay, 1 and 8.
Mm-hmm.
And and I think the reason there are actually 16 of these different depictions of the ways the planets can orbit, the number 17 is the same as 1. Okay?
Mm-hmm.
So there's 16 different ways. It's the 8 ways that are within the periodic table or the Pulaski atom and times positive and negative.
Mm-hmm.
And so these are just showing that you get, for example, you go through where these different nodes and positions of the planet's relationship to the sun, and you get, that's the mirror opposite, and then you come right back around to number 16 or 17, I guess, which is the exact mirror.
Yeah.
And so what the question is, what describes these curves here? And it's both positive and negative described, and this encompasses the retrograde motion and the fact that the positive energy is greater than negative energy, etc. And this is pretty new. So, for example, he says, under the figure, the different possible shapes of an opposition loop. The position of the planet at the instant of the opposition with the sun is indicated by a small circle. The shape of the loop depends on the position of the planet with respect to the line of nodes of its orbit at the instant of opposition. The first case occurs when the time of opposition the planet passes as the ascending node. The cases 2, 3, 4, etc. take place at ever increasing celestial longitudes, and type number 17 is merely a repetition of type 1. For the planets Jupiter to Neptune, the opposition nodes are flatter than those of Mars. This is very indicative of a negative field there rather than a positive field. So it never ends, but I've got to get it published, Robert. So that's all, I guess. Right now I'm about ahead of it, I guess.
Okay, we've listened to Paul
So there-
A. Williams, and Levon Williams Finlayson's been doing commentary, and Robert Tode, what is it? Todos? Todos Zalewski
From Warsaw.
from Warsaw, Poland,
And
is
his
here
address.
after 9 years
9 years since I saw Robert.
since he saw anything that Paul showed him. But he's a bright young Polish man.
But give
Young
him
man.
his address, Polish address.
It's changing.
Changing, I was going to say.
Oh,
Maybe
It's
maybe
not valid next year.
okay.
So they still have Sawadis over there, right?
So
Huh?
is that it then?
Well, for today, I don't know.
Yeah.
I think there's a lot more that. For example,
I
Rob,
like the spectrum.
you got that same book?
No,
Oh, see what I've done with this, and this is.
this book is
I've
not
gone
translated into Polish as
Oh,
far as I
well,
know.
it's a classic. But what I've done, Robert, is I've got, for example, I figure when I get meeting with professors, etc., that the red, for example, the red is all the long wavelength. This particular note right here says inverted spectra. Well, how did it get inverted? I mean, there's a negative field there, and so this is all cross-referenced. That if I get into a bash, if you want to say that, then I can turn. I've gone through about 3 of these books.
That book there, you've done through
Oh, yeah,
Hatfield?
yeah.
Alright, so that's.
The 3D shell lies somewhat above the 4S shell. See, what this is talking about is potassium.
We were discussing this 9 years ago.
That's right. With increasing Z, the 3D shell tends to be lower. Eventually, it is lower than the 4S shell. That's the air of the sliders.
No.
So,
Well-
I've got it all cross-referenced. But see, I couldn't remember where we left off. But I wanted to
On that one. On the
on
spectrum.
the spectrum. Yeah. See, and we probably once you hand me we
Well,
probably could go through another session.
yeah. Well, listen, this is taking place at 1632 East Elmwood in Mesa, Arizona. That's the residence of Richard and Levon Finlinson. And do you want to hold up Helen's Pulowski's
Yeah,
model?
that's a
This is her book, the Visualization of the Atom, and open it up to show the model that Paul's been referring to, the periodic chart. Let me zero
which we call
in
the
on
pattern
that.
of
This
creation.
is the periodic chart / model of the atom, and that's the basic model that Paul's been basing all of his research on.
What
Okay.
I could review a